Okay, so I'll get it going. So there's quite a bit of things to cover. Okay, so good afternoon. I'll be taking the tutorial. It will be the last tutorial for your module. It will be a combination for polymers and hydrogel because they are more or less within the same category when we talk about materials. Okay, so this is my email address again. So any questions you have, you can just send me an email. Anything I can't answer, I'll pump it up to Paul Bertrand and reply from there. Okay, so you have went through your polymers and hydrogel tutorials, lectures for the past 2 weeks. You had your hydrogel this morning. Okay, so for polymer lecture, once again we are talking about this specific class of material polymers in terms of its behavior in the biological settings. So sometimes we term them as like biopolymer, just like bioceramics in the previous chapter. Okay, so in the lecture you are given a recap of polymers, what are polymers, the different ways of polymerization and how they differ and what are their properties. Okay, so then some of the biopolymers we talk about their properties, which we have learned about it, and what requirements there are there for them to be used as a biopolymer. Okay, and the next important thing for polymers is actually sterilization, right, which is the method to make the material sterile after your manufacturing. Right, so once you make a new material or you get a material, you want to use it as an implant or in a biological setting, you have to make sure that it's sterile so that it doesn't introduce pathogen or bacteria. And sterilization is more important for polymers because you would know that for polymers, right, their properties are usually not as ideal compared to ceramics or metals. So the type of sterilization that polymers can go through are much lesser, and they vary by more within the whole category of polymers compared to like ceramics or metals, which can undergo almost all kinds of sterilization. Okay, so here in this tutorial we'll be covering sterilization. So let's listen up for it. And then degradation and their biomedical application. Right, so polymers, when we previously talked about biodegradable material, a lot of times we are referring to polymers because polymers, under the class of polymer, there are more examples, right, that are biodegradable. Okay, and then for your hydrogels, right? So hydrogels, in terms of structural and property, they are very similar to polymer, and in fact, hydrogel is actually a subclass of polymers, right? So there are different classifications of hydrogel that you have learned, right? And the key property of hydrogel is that they can swell or de-swell in a wet or dry environment, right? Which is the swelling property of hydrogel, right? So it is very important here because it is this property that we classify this material as hydrogel. And how we use that in terms of advantage, right? In terms of any biomedical application, drug delivery, is basically all based on this swelling property, right? So you have to know what this property is about, how it varies, what the calculations you have to do for the swelling property. Okay, and then of course the application, the classification of natural versus synthetic polymers, advantages, disadvantages, and your two examples, polypeptides and polysaccharides, which are proteins and your sugar. Okay, so jumping on into your tutorial, right? The first question gives you a whole list, right, of numbers and asking you to find a different molecular weight. So here for molecular weight, there are two different that we are talking about. Number one is the number average. So number average is the most intuitive way of calculating average, which you guys have been using, right? So you just take the total number of molecules per weight and you just divide by the total number of molecules. So what this does is it gives you an average on the number of each type of particles, regardless of how much they contribute to the average. Okay, so you just number of each, you multiply, divide by total number. The other one is weight average molecular weight. Okay, so weight average molecular weight, the calculation is slightly different, and it takes into account how much each type of molecule contribute to the whole average. And this is how we do that is take their weight average over the total weight, which we will look at later on in all the calculations. Okay, so both are giving you average, but they are representing a slightly different thing. And with when we have a polymer solution, right? You know that there is a distribution of different chain lengths, right? Unless we are not talking about monodisperse. If it's monodisperse, fine. You only have one kind of chain length. But for a polydisperse polymer solution, you will usually have a distribution of different chain lengths, which has different individual weights. So a weighted average is actually what is more commonly used. And if you plot them into the same graph, right, usually the weighted average, the weight average, molecular weight, is slightly to the right of the weight average. Okay? So the calculation are as follows. Summation, a lot of numbers, but it's actually quite straightforward. For number average, you just take the summation of the number of each type of molecule multiplied by the individual weight. You sum everything divided by the total number. Here, you take into Wi, which is the weight fraction of your each individual polymer. How that differs, we will look at the calculation later. Okay, so and when you have these two numbers, right, if you divide your MW over MN, it will give you the polydispersity index, which is the index or number reflecting how dispersed the solution is. Okay, so for PDI1, right, it means a monodisperse, there is only one chain length of polymer in the whole solution. Okay, and for that to happen, your MW has to be equal to your MN. Means regardless, if I take just the number average or the weight average, their weight fraction is still 1 anyways, because there's only one type of weight for solution. Okay, and usually for very controlled manufacturing processes, usually in real life, the best we can always go is 1.0 something to even 1.1, which is already very good. Okay, because as you know, if you go about different type of polymerization, it's very hard to control the length and when to stop for every single reaction. Okay, so usually it's very hard to get exactly one. Okay, so for the question, you have a whole chain of number each number of molecules of each mass. You're asked to find the number average. So number average is pretty simple. You just take the mass of each molecule, multiply by how many of that molecule you have, and then you just sum everything together, and you divide by the total number of molecules. Right, it's a very simple calculation, but it just involves a lot of zeros. Okay, so just be careful for this during your calculation. Alright, and just plug out the numbers, you get Mn to be 507,600. Okay, nothing complicated. Any questions for this? Anna? Okay, but for MW, it's slightly more complicated. So there are two ways, right, that you can calculate that I've shown you. One is either you go through the weight fraction. Number two, if you don't want to memorize so many different things, okay, you have this formula, you just plug everything inside. So I have to make sure you know how to do it. Okay, so let me show you. First, is either you calculate the weight fraction. So how you calculate the weight fraction is you have to take the total mass of that type of molecule. Meaning to say if there are two of this molecule with this mass, you multiply by 2, this is the total mass of each type of molecule. Right? And then you divide that by the total weight of the whole system. Then you will get a fraction that is representative of that kind of weight over the total weight of the total mass of the solution. Meaning to say the weight fraction is a fraction out of the total mass of the whole system for that specific type of molecule. Okay? And if you have that, right, you can just multiply back to the mass of each molecule and then just sum everything together. Okay? Then you should get 538,630. Okay? Okay? Or you just go by this formula, you just plug everything inside. Right? Ni, you got Ni, which is the number of molecule, Mi, your mass, and you just square the whole thing. Right? Ni Mi squared. So Ni Mi squared is this times this, and this thing you take the power of 2. Right? And you get a whole chain of numbers. I've already taken out 12 zeros from here, so that's why it's all one decimal. The number is from 1 to 10. So be very careful of these type of calculations because it involves a lot of zeros. Okay, so you just sum everything together, you divide by the total mass of the whole solution. Okay, you will get the exact same number. For those who are more mathematically inclined, you can actually work out the previous formula. If you know the formula for weight fraction, actually works out to be equal to this. So it just depends on which method that you can understand better or more comfortable with, and then just go ahead. Okay? Clear? Any questions? Okay, good. So PEI, MW over MN, okay, nothing much about it, so it should be 1.06. Okay, so usually we are given a chain of number. The question will just ask you to find the PEI of the solution, right? Then you have to know you have to calculate the MW. Okay, yeah. Okay, so for question 2, right? So you are given styrene oligomer with 48%. You have the Mn. You mix with another polystyrene. You have another Mn. So what is the Tg of the whole system? Okay, so here, this is how you find your Tg. Okay, so this is, I think it's from your lecture notes. Right? So this is a formula that we given. So the Tg of the system will be this Tg infinity, right, minus your K divided by the number average. Okay, so but now you are given 2 is a mixture. Right? You know how to find the Tg of an individual component. How do you find the Tg of a mixture when they are both added together? Okay, so first, you need to find the Tg of individual component first. For the styrene oligomer, right, you have your polymerization of 6. So in order to find your number average, you have to multiply the molecular weight of, is it given? Yeah, it's not given to you, but anyway, it's the molecular weight of each individual repeating unit. Oh, sorry, it's given to you. Okay, so you have the M0, which is the molecular weight of each repeating unit. Right? You multiply by the degree of polymerization, which is 6, you get Mn. Okay, so this formula is what you need to know. So with your Mn, it's a matter of just plugging all the numbers together. K is a constant, right? Tg infinity is also a constant. Okay, so just plug in your calculator, and you'll get the Tg of the styrene oligomer to be 181 Kelvin. Okay, so M0, if it's needed, it will be given to you. You don't have to memorize the repeating unit molecular weight, so just take note. Okay, so next. Now, how do you, so now you got the Tg of the first component. How do you find the Tg of the mixture? So this is what you have to go to, a Fox equation. Right? So the Fox equation determines, or rather it defines how you would be able to find the Tg of a mixture. So what it says is that the inverse of the Tg itself will be equals to the weight fraction of the individual component divided by the Tg over the individual Tg of the individual component, and you just add everything up. How we do that? So first, we have found Tg1, right, which is the first component in the previous part. So to find the Tg of the second one is the same thing. All the numbers are given to you. Just plug everything inside, you get 372. Now you have Tg1 to be 181, and you have your Tg2 to be 372. So what is the Tg of the overall mixture? So going by the Fox equation, first you have to find the weight fraction. So how do you find the weight fraction? If you look at here, so the styrene oligomer accounts for only 40% of the whole mixture. Meaning to say, out of the whole mass or weight, 40% is the styrene oligomer, which means the weight fraction will be 0.4. Right? Okay, so weight fraction is always from 0 to 1. Okay, so it's 0.4. And the mixture only has two things, the styrene oligomer and the commercial polystyrene. So if 40% is the styrene oligomer, the other 60% has to be the second component, which means the second weight fraction will be 0.6. They have to both add up to 1. Okay? And then you just solve this equation to, then you can find out Tg to be 261 Kelvin. Okay? So I'm not going to go into the nitty-gritty calculations. The key thing here is you have to, this formula you have in your lecture notes. You just need to remember this Fox equation. relationship. And this can work for a mixture of 3, 4, or 5 components. You just add on to this equation. So if there's 3 components, it will be W1 over Tg1 plus W2 over Tg2 plus W3 over Tg3 plus W4 over Tg4, so on and so forth. Right? Until however many components you have. Okay, clear? So one key mistake is sometimes when some students will put the weight fraction as 40, right? So just remember you have to convert it into decimal. It's from 0 to 1. Okay? Any questions? Okay, nice. Okay, so before I go to question 3, right? So to remind you of the swelling property of hydrogel. So like I mentioned just now, the key property of hydrogels is that it can swell in a wet environment, and when you dry it, then it will dissolve, obviously. Okay, so when there is swelling involved, what happens is there is a change of volume because the hydrogel itself takes in the solvent. Right, so in most of the case, we are talking about water, right? But it need not be water. So here I'm just talking about solvent, because as long as it is in any suitable solvent, it can swell. Okay, then later we will look at something called the interaction parameter. Okay, so when you talk about swelling, when it's in the unswollen state, the initial volume will be V naught, right? Once you're swollen at equilibrium. Okay, so I have to mention this swelling property is not unlimited. So it won't swell until it bursts, that kind of thing. It's not hyperbolic. Right? It will when it starts to swell, it will eventually reach an equilibrium state where it stops swelling. Right? And at that point, that final volume will be your Vf. And that volume consists of your V naught, your individual volume, and the amount of solvent that is actually taken into the hydrogel. Okay, so there is a limit to how much it can swell, and this limit, right, is what we term as the swelling ratio. The ratio of the final volume at equilibrium over the initial volume. Okay, so you can, in a sense, it's in simple terms, it will be like how many times it can swell at maximum. Okay, so if it's 40 means when I put it in water, it can swell to 40 times the initial volume. Okay. And the inverse of this swelling ratio is your volume fraction at equilibrium. Right? The key thing here is at equilibrium. Okay, so if I'm going to study the swelling property of hydrogel, usually you put in a suitable solvent and you give it enough time to reach swelling equilibrium. And then you take the swelling ratio and you know the volume fraction, which is your phi to equilibrium. Okay? Any questions? Okay. And then, whenever we talk about swelling property of hydrogel, you have to go through this Flory-Reynolds equation. Okay, it's got to be one of the most complicated looking formula in this whole module, but it actually just involves 4 different variables. Right. So number 1 is your interaction parameter, which is your now it's called chi, right? Let's call it x. Yeah. So your x is your Flory-Huggins interaction parameter between your polymer and solvent, meaning to say how well the solvent interact with the polymer itself. The higher the number, the better it interacts. The more of the solvent it will take it in. Right? So it's quite intuitive thing. And then the next thing that is determining is will affect the swelling property is your N, which is your cross-linking density. So here you have to understand that in a polymer or in a hydrogel structure, we are talking about a cross-link network, or sometimes we term it as a mesh network. So cross-link density by definition is like how close are the cross-link points from each other on average. So if you look at it like in the term of a fish net, right? A net with a higher, if you look at it, for a polymer with a higher cross-linking density, if you imagine, which means the netting, the crosses of the net are much more closer to each other, which means the hole in the net is much more smaller, if you can imagine it that way. So if the crossing density is lower, the distance between each cross-linking point is bigger, the hole of the mesh is bigger. Right? You can imagine. right? So which is why the n is in negative bracket. So the higher your cross-linking density, the lower the swelling will be. Because if your cross-link density is high, right, all the cross-link points are very close to each other, and the cross-link point cannot be disrupted just by swelling, right? So if they are all very close together, the amount, the volume that the whole network can increase is very little. All the points are very close to each other. It's just like a net with very, very small holes. It's very hard to stretch it apart. On the other hand, if the cross-linking density is very low, which means the cross-link points are very far away from each other, I am able to stretch the net to a much greater extent, which means the swelling probability will be higher. Make sense? Right? Okay? So that's why it's in a bracket. And then you have your solvent molar volume, which is a property of the solvent, so nothing much about it. It's just that per mole was the volume. Okay? So this is a property of the solvent. It will be a constant. Most probably will be given to you, unless you're asked to calculate this. Okay? So 1, 2, 3, and of course your volume fraction and equilibrium, right? Remember this? Right? So if you look at this equation, if in a final exam this kind of question comes out, you just have to identify 3 out of 4 of the variable. You can just easily solve everything. Right? Although there's ln, there is square, everything. If you have all the individual value, right, you just plug it in, you just be a whole chain of numbers. Right? Nothing complicated about it. Okay, so but one thing you need to note is I'm not sure whether Prof told you in this lecture, you will probably need your scientific calculator during your final exam. Did he mention that?
Yeah.
Yeah? Okay, so remember, because especially for this kind of calculations, or even the one for PDI, you have a lot of numbers, a lot of zeros, and kind of thing, so you've got to be careful. Here is because you have a natural log, so natural log is not something you can write down in calculator, which is why you need a scientific calculator. There's no need for a graphic calculator, just a simple scientific calculator will do. So make sure you have it. You should have at least one, right? I'm not sure whether now you still need to get it certified or whatever. Just check MSc, huh? Okay? And with your scientific calculator, it will be a very easy punching of numbers. Okay, so if you look at this, so at equilibrium now we can tell that the swelling property is, the swelling of the polymer is dependent on two things. How close the cross-link points are away from each other, and how well the polymer and solvent interact with each other. Because the other two are material property. Right? Your volume fraction and equilibrium, this is a property of the hydrogel. Your solvent molar volume is a property of the solvent. So these two things is what will actually depend or affects your swelling. Okay? So let's look at one of the questions using this. Alright, so you are giving polybutylstyrene swelling ratio, toluene, so what's the modulus? Okay? So number one, what are the things you have? So first thing I have a swelling ratio. The moment you have the swelling ratio, you can find the volume fraction. Okay? So all this will just become a number. Right? Chi is given 0.339. Right? And so what you're left with is your cross-link density and your molar volume. Solvent molar volume, which we will see how we will find. Okay, so you're already given 2 out of 4 variables, so let's see how we can find the other 2. So like I said, once you are given your swelling ratio, you can find your volume fraction equilibrium. It's just a matter of taking the inverse. So next, you need to find your molar volume. So like I said, molar volume is the volume of 1 mole of the solvent, which means the unit will be volume per mole, or your ml per mole. So looking at the units, what is the thing we have here is, the only thing we have here is density. So density is grams over cm cube, right? So cm cube, which is also your volume. So we will need something that is grams per mole. Then we can cancel off the grams to be cm cube per mole. And grams per mole is actually your molar mass, right, of the solvent itself. So here, toluene molar mass is 92. I think it's not given. We supposedly wanted you all to find online. But anyway, for the final exam, it will be given to you. Right? So you have your molar mass, which is grams per mole. When you take grams, if just by looking at the units, you take grams per mole divided by grams per cm cube, you will just be left with cm cube per mole, which is the same as your ml per mole. Okay, so that's how you can get it. Okay, so with V1, you just substitute V1 to be 106. Volume fraction, all the volume fraction will become 0.208, and your chi is 0.39. So now you are just left with n. Right, so you just have to plug all the numbers into your calculator. You can solve n with 1.6 times 10 to the power minus 4. Okay, so in between I skip a lot of steps. It's basically just plugging all the numbers in and punching into your calculator. Okay? Yeah? Okay, so next, so how do you find the modulus? Okay, so this is the relationship. So modulus of hydrogel, right, it depends on your shear modulus. Or rather, the shear modulus depends on the water content. So the relation is given your shear modulus G is equals to nRT, R being your gas constant. Okay, T temperature and cross-link density. So take note, for gas constants, in your list of formula, there are a lot of different numbers for gas constant. Need to take the correct one and the correct units. So just plug everything in, right? And Young modulus is 3 times of your shear modulus, right? So with that, just a matter of putting all the numbers in, you get your E equals to 1.19. So 3n RT, 3n is what you gotten in the previous part, right? Your crossing density. R is your gas constant, 8.314. Just take note here, if you are not sure which number to get, sometimes you have like 0.8314, that kind of thing. So you have to just look at the units, right? You need to be able to cancel everything except for your Pascal. Right, so cm cube, I can cancel off. K, I can cancel off with the, here, mole I can cancel off. So you're left with P. So 8.314 is the correct one for your gas constant. Right, so this is just something to take note. Okay, then you just simple solving to your calculator, you can get your 1.19 megapascal. Okay? Clear? Any questions? So it's slightly more mathematics involved here, so just take note of the calculations. And in fact, this can be combined with the previous ones, which is the Fox equation. There are questions that involve both, so you have to be sure of both concepts. Okay? Any questions? Okay, good. Right, so for question 4, right, here you are given a synthetic copolymer, your PCB It was chosen to develop a DDS. So here, this is a synthetic copolymer. Whenever you have this poly something, most of the time it's synthetic. It's what we make in manufacturing. So on the other hand, for natural polymers, we are talking about things like that come from natural sources. Your chitosan, your collagen, that kind of thing. Okay, so here is asking you what advantage does it give and why the shape is important. Right? Number 1, so it's just asking you about synthetic versus natural. So synthetic, right, it has a much better availability because as long as we have the raw materials, we can make it anytime. Uniformity, whenever we have manufactured processes, most of the time we will go for uniformity, and it's much more achievable than when you take from natural sources. Because in nature, the variance, the variety of different material, the variance, the variety is very huge. It's very hard to get a very uniform material out of nature. So uniformity definitely much better when you are manufacturing your factory. There's no Harvard surgery, right? So especially if you remember the previous, we talked about heart stent and all. If you want to take something from nature, especially from xenographic or even implant or whatever, whenever you involve Harvard surgery, you will have morbidity, right? A risk of failure. And when you want to harvest from external source or different species, you have an immunogenic rejection to worry about also. Okay, so for synthetic, there's no such issue. It's just something you manufacture from the factory, sterilize, and you can use. Okay, and then reduce chance of disease transmission. Okay. So this is just for example, one of the popular example of natural polymer will be collagen, which actually if you look down into it, it's amino acid chains. You become alpha chain, you become a helix, then you become fibril, then you become a collagen bond. Okay, so this is just for your knowledge, you don't have to draw it out, so don't worry. For your PCPPSA, right, this is your structure. When I talk about copolymer, if you remember, this is actually a co-block polymer, if you have to look at it that way. So it has two different types of monomer repeating unit. One is your succinic acid, and two is your CPP. So these two, they are mixed together in a certain percentage, giving you the copolymer. But why is this used? Or rather, how, when we use this in DDS, what is an important consideration, right? So, which is the second part, which is shape. And why shape will be an important consideration is because of how it will degrade, especially for this PCPSA. When we talk about degradable polymer, the shape comes into play. So first, but before I go to that, we have to understand how this material degrades. So the copolymer degrades by the cleaving of the N-hydride bond. And cleaving of the N-hydride bond is fine. The key thing here is because this copolymer involves two different components, like I mentioned. And one component is actually hydrophobic, and the other component is hydrophilic. And because this undergo hydrolysis, how well the water can go into the material will determine the rate of hydrolysis. Right? So if I have a large chunk of my CPP here in the whole polymer, where I only have a little percentage of SA, overall the hydrophobicity is there. Water is very difficult for water to penetrate through the material. The hydrolysis or the degradation will be limited thus to only the surface. Right? Because of the overall, or unless you have a huge chunk of SA, but if you look at here, another thing is the size of the repeating unit. So in a copolymer of such, right, because of this hydrophobic CPP, right, it will have a certain barrier for water to penetrate through. Right? So whatever the level of water penetration is low, so all the hydrolysis is limited to the surface. And this kind of, especially we talk about these poly anhydrides, they usually undergo surface degradation. So this will then lead to the importance of shape. Why? Because what shape I have will determine the amount of exposed surface area I have. We try to look at here. Because, so the key thing first, it has to undergo surface degradation. So for material that undergoes bulk degradation, shape is not an issue, right? Because water will just ingress into the whole material, the whole bulk of it will just degrade at the same time. Because it's surface degradation, now the surface area matters. How it matters? Given the same volume or unit volume, by just having a different shape, the amount of exposed surface area will differ. What do I mean by that? So let's say you look at a unit volume of 1, right? If you look at a unit volume of 1 in a cube, in order for the unit to be 1 meter cube, each side of the cube has to be 1, right? 1 meter. And each side of the cube is 1 cm, or 1 meter square. 6 sides, 6 meter cube, correct? 6 meter square, correct? So when we look at the surface area to volume ratio, the surface area of a 1 meter cube, right, of shape, of a unit volume with 1 meter cube, for a cubic shape you have 6. Because 6 sides, 1 meter square each, you divide 6 divided by 1 is 6. But if you look at sphere, right, the unit to finding a volume of sphere will be, remember, how to find the volume of sphere? 4/3 pi r cube. Okay? In order for your 4/3 pi r cube to be 1, because we're talking about unit volume 1, right? If you just work backwards, right, to find your r, right? Then you find the surface area of sphere, which is, what's the formula for surface area of sphere? 4 pi r square, right? So from there you find a 4 pi r square, you realize that it's actually 4.83. Which means here both have the same volume, but because of their different shape, they have a different amount of exposed surface area. And if I know that it undergoes surface degradation, which one will degrade faster? The cube or the sphere? Make a guess?
Sphere.
Why?
Small surface area.
More?
Less surface area.
Less surface area, so you will degrade faster. It's in fact the opposite. So because you're right, the sphere has a smaller surface area per volume, but now here we have a material that undergoes surface degradation. The more exposed surface area it has, the faster the rate of degradation. Right? Because there are more area for the water to attack on for hydrolysis to happen. You understand? Alright, so if with the same volume, by just changing the shape, I have different surface area. The larger my exposed surface area, the more points of attack by water or the hydrolysis can happen, the faster the degradation. Because it's surface degradation. Okay? And in fact, sphere is actually the one with the smallest surface area to volume ratio. So if you look at this, if you find all the surface area to volume for all, this is area to volume, you realize that sphere actually has the lowest. Okay, and the lines, there are two things to take note. The lines will never cross each other. Meaning to say, at a certain volume, the ranking of the surface area of each shapes, right? The ranking will just stays the same for all the different volumes. Okay, not the dotted line. The dotted line is just the 1-to-1 ratio. Okay, so if you have for different color, you don't cross. Meaning to say, how you find the relationship is if you are given two different shapes, right? And one of them being sphere. Right? How you can understand is here. Again, you just need to remember sphere is always the one with the smallest surface area. So how do you remember is if you have anything compared to a sphere is always smaller at any volume. Right? If you can't remember, you just do this simple calculation. Compare a sphere to a cubic, and then you remember, oh, sphere is smaller than cubic. Then you can remember the relationship, sphere is always smaller than anything. Okay? So please, you don't need to memorize all this, but the trend here is that the ranking stays the same, and the sharper the edges you have, right, the larger your surface area to volume ratio you have. And the one with no edges, the shape with no edges is your sphere. Right? So it all ties together. So you can see here your three-sided pyramid, the corners are sharper than others, right? Okay, so these are generally why the shape is important. All this will not matter if the degradation is bulk degradation, right? Because if I have bulk degradation, then the surface doesn't matter. Right? The water will penetrate through regardless of the surface. Then the next thing that is important is just how well the water interacts with the water. Okay? Any questions? Yeah. Okay. So this is just to show you like there are certain things that are important during your design to consider during the designing stage, like shape and all, which actually ties into their property. Right. So there's something for you. Okay. Next, question 5. You are asked about the sterilization for polyethylene. Okay. So when we talk about sterilization, we are referring to the complete elimination of all forms of microbial life. It is different from your sanitizing your hand or disinfection. Right? Those we are just talking about the removal of a good amount of microbes. When we talk about sterilization, it's 100% the complete elimination of all microbial life, because we want to more often than not because the material has to be used, right, in vivo. Meaning it has to be interacting with either cells or tissue or organs, right? So there is no one method for all polymers. What I say here polymers is that for ceramics and metals, usually they can almost all types of sterilization can be used on metals and ceramics because their general properties are stronger. They can withstand a much wider range of conditions. But for polymer, they are not, so you have to be more careful. Okay? Then we'll look at what are the things that will affect. Number one, okay, the first method of sterilization that we talk about is your dry heat or steam sterilization, sometimes also known as your autoclaving. Right? Basically, it just means I throw my material into this machine, we ramp up the temperature in presence of water. So high heat and high in the presence of water will kill off all the microbes and bacteria. Right? Because no microbes can withstand this kind of conditions. Right? And usually the temperature we go to is way past the boiling point of water, which is why sometimes known as steam sterilization, because all the water will be your vapor state. Okay, so if you look at the example of PE, there are different kinds of PE, right? Polyethylene. So we just have to compare whether or not the ultra high UHNPE is suitable. If it's not suitable for the ultra high molecular weight PE, you don't even need to talk about the long chains or the low density that kind. Okay, so for ultra high molecular weight PE, the melting point is around 150. Definitely not suitable for use because the temperature ramp up is way past the melting point. For sterilization, the key thing here is I only want to kill off the microbes. I do not want to affect the material property. The material that goes in and comes out has to be the same in terms of the property. Okay, so as long as there's a chance of melting, right, definitely not suitable. And even if we lower the temperature to be lower than its melting point, PE is still not suitable for use, for extended use for a temperature higher than 100 degrees Celsius. And because for this autoclaving, usually it's in terms of number of hours. So it's not just a 1-2 minute kind of thing. So with that number of hours at this high temperature, your ultra high MP will definitely not withstand this condition. The property will be affected, then there's no point in sterilization. Okay, so first method, not suitable. Next, we talk about radiation. So radiation is just using the different electromagnetic waves to just penetrate through the microbes to disrupt the DNA and kills it from within. Okay, so this is in terms of penetrating strength. You have, of course, your common UV, your electron beams, gamma ray, and your X-ray. But this is also what X-ray is used to image your bones, because it can basically pass through. Okay, so it disrupts the DNA, right, and you kills the bacteria from inside. Okay, so so looking at the ultra high molecular PE again, what we are interested here is always whether or not its material property will be affected. And if you look at this, radiation will affect its fracture toughness, right? Which means when going come out, it might be more brittle than when it goes in. And if it even causes further cross-linking, definitely it's not something we want. Especially for material that is, or for polymer that are being formed through photopolymerization. Further radiation is definitely not encouraged, right? Because we do not want further cross-linking. Sometimes, yes, further cross-linking might seem like a better thing, right? Give it further cross-linking, make it stronger, thing like that. But no, in terms of sterilization, because we do not want any change in material property. Regardless whether will make it become stronger or weaker. Okay, so yeah, any questions? So the key thing here is you have to compare the different methods of sterilization and to see whether or not their material property will be affected. Okay, so other than that, we have the next one. We also have sterilization by EO gas, ethylene oxide gas. It is just an exposure to EO gas, which is toxic and will just kill the bacteria. It is in either moisture or solution form, or sometimes you can even have it in gas the gaseous form. So it's quite flexible. And the other one is your hydrogen peroxide gas plasma. How it works is, you don't need to go into the details about it. You need to have a seed gas, right? And then you expose the seed gas to very high frequency or microwave, and then you generate a free radical. And that free radical will just attack the microbes and will kill it from there. Which is why for materials such as PE, which is much sensitive to the harsh, to those harsher conditions, these two methods is what actually is more suitable for your body. Okay? But for gas plasma, it's weak penetrating, so that if you have a material which have an intricate design, right? If you have holes and things like that, because of the weak penetrating power of gas plasma, you may end up just sterilizing the surface, but if it cannot penetrate to within, like let's say you have a box, for example, but if you just close the box and put it into the sterilization, the surface might be sterilized, but not the inside of the box. Okay? Which is why, so most of the time for PE, we will use ethylene oxide gas. Because if we put it into an EO chamber, the material get exposed to the EO gas, will more or less be able to sterilize the whole material inside. The only issue is that it's toxic, right? So you need to make sure that you have enough time for the gas to dissolve. I mean, because the gas will not be absorbed into the material, it will just be a sterilization. As long as you have a long enough duration time, which is the time allowed that you leave for the gas to dissolve, it will be suitable to be used for most material. Okay? And especially if you do not know whether the polymer can or cannot withstand the heat or radiation, usually just go for EO gas. Because EO gas won't affect the material property. The only thing is just the emission time. Okay? Clear? So here, for this question, EO gas. Any other questions? Yeah? A little bit of memorizing involved to just take down. Okay, so last two questions. How does hydrogel is used in tissue engineering? Remember what's the three things that are needed in tissue engineering? Cells. Come on. Cell, scaffold, environment, right? So for cells, definitely you can't do anything about it, right? So most of the time, hydrogel is either used in the scaffold or the environment to help with the environment. Most of the time, scaffold. How? By making injectable scaffold. Because hydrogel can be slightly more fluid, you can't able to use as an injectable scaffold. Okay, something like this. So what you can do is instead of cutting open the skin, putting the implant in for tissue, sometimes you can have an injectable. You just have a needle, you inject a good amount of hydrogel in, and then you can cure it from using UV. UV can pass through your skin to a certain degree, okay, or other radiation. You cure it, then you will form a scaffold. Okay, so this is actually an example that's what is used commercially. Okay, so instead of always imagining scaffold to be a hard solid, you have to cut open and put it in. Sometimes you can have like semi-fluid material like hydrogel to use as an injectable. And injectable, why is it good? Less invasive, less risk of morbidity, things like that. Okay? Or sometimes you might even have a composite of osteoconductive material, such as your calcium chloride. Right? By having it in terms of these beads, here are your TCP beads, remember your TCP? Right? It is treated with CaCl2. TCP itself is biodegradable, and when you introduce your calcium chloride, it becomes osteoconductive. So meaning I have a scaffold now that is osteoconductive. It can draw in the osteocytes for bone growth or even become a bioactive scaffold. Okay, so this is just an example, right, to trigger your thinking of how you can be creative using hydrogels, right, in terms of for this scaffold in different So you don't study about hydrogel just because you can swell. Alright, you can definitely apply it to things like tissue engineering or even drug delivery. Right, so this I won't go into detail. I've already explained it in the drug delivery tutorial. How we use polymer or hydrogel in tutorial. We have talked about this, right? The spark responsive polymer. There are polymers, or rather hydrogels, that can respond to different kind of things. Meaning to say, it can swell when you have certain triggers. Right? For example, like your knee pump, where you can swell, it will swell when there's a temperature change. Or most commonly used is your pH responsive polymer. When you have polymer that actually is protonated at certain pH, when there's a pH change, once it suddenly becomes protonated, it will swell. You cause the crossing network to be expanded. Right? Or you can always have your degradation, degradable material. All this, what we are trying to achieve is a certain level of control on the release of drugs. Remember, drug delivery, we are delivering and releasing drug to achieve the control in some state. So here, when we have a trigger, if I know you respond to pH, I just need to control the pH, then I can trigger the release. Remember the example that I give where in cancer it's a lower localized change in pH. You can make use of that, use a pH responsive polymer to trigger the release, only at the localized low pH. Okay? Then of course, instead of using it as a hydrogel, you can use it to form a vesicle, what we call polymersomes. So polymersomes are like, each red and blue is one molecule of your polymer. The red and red will actually interact with each other to form a 3D structure, like a balloon or a ball, hollow ball. So you can hold different things inside. Things that are hydrophilic, you can hold inside. Things that are hydrophobic, you can hold within here. And you can even attach stuff at the surface to give it certain property. Right? So you don't need to know about the science of all this. They are just an example for you to, if let's say you are asked to suggest a certain way, right, these are a few things that you can suggest. About hydrogel or your polymersomes. Okay? Any questions? Okay, so all this, just have to know that there are distinct